Good morning, ma'am.
Morning, Elia. How are you?
Fine, ma'am. Ma'am, how are you?
Fine, thank you. Hello, Nimra.
Assalamualaikum,
Assalamualaikum,
ma'am.
ma'am.
Walaikum salam. How are you?
I'm fine, ma'am. How are you?
Fine, thank you. Hello, Halima.
Assalamualaikum, ma'am.
How are you, Halima?
I'm fine, ma'am. How are you?
Fine, thank you. Hello, Aruba.
Hello, ma'am. Assalamualaikum.
How are you?
I'm good. How are you?
Thank you. Hello, Sahib.
Good morning, ma'am.
Morning. How are you?
I'm good. I'm good.
Okay, great. Okay, so we are going to start. I'm going to first take the attendance. Okay. So I'll mark the names that are present. The rest are absent, right? So Nimra is present. Sahib is present. Edia is present. Aruba is present. Halima is present. And that's it. Have I missed any name that's present? 5 people are present at this time.
Ma'am, your voice is not clear.
My voice is not clear. Okay, can the other students hear me? Hmm? Can you all hear me? Hello, Saul.
Hello, ma'am. How are you?
Fine. Yeah, can you hear my voice?
Yes, ma'am, but it's very low, ma'am.
Okay. Okay. So today I'm going to share with you the text, okay? Okay, so you can see the book now.
Yes, ma'am.
We are going to study chapter number 5, okay? And for this purpose, this is a very interesting chapter, and you must have seen a lot about this regarding most of the sci-fi movies, are exploring topics like this. So this is about the cosmos, right? So what is the cosmos? The cosmos is, you've heard the word cosmos, right? You've heard the word cosmology. You've heard the word astronomy, right? You've heard words like galaxies and constellations and stars. So this is a very interesting. There was a very interesting series of documentaries called The Cosmos. It's very simple to understand. You don't have to be an expert in physics to understand it. In fact, children can understand it. So you can see a lot of very interesting videos about this. So this is a study of the universe, right? About how the universe started, for example, the different galaxies we have in the universe, the different laws related to this, and the different concepts related to this. So again, I know that many people are fans of sci-fi movies. You don't have to be a physicist to be a fan of sci-fi movies. Again, when they show such movies or documentaries or videos, normally they're made at a level that's very simple and everyone can understand. So one good source of information can be NASA, for example. You can check a lot of nice videos, animations, images from NASA. They're free of cost and you can explore.
Excuse me, ma'am. मैम आपकी आवाज़ बहुत कम आ रही है, स्लो आ रही है।
कौन बोल रहे हैं?
साउल रफाकत मैम।
Okay, so now I'll start again. Okay, so we are talking about this chapter, which is about the cosmic engine. Again, this is related to topics related to cosmology. It's you must have heard terms like the cosmos, astronomy, NASA. So this is about the study of the universe. You must have heard about the Big Bang, for example. So we will talk a little bit about this. Okay, and also you must have heard about the stars, the galaxies, the constellations, and various terms and laws of physics that are related to this. So this is what we are going to study today. So when we talk about this, of course, like you are familiar with groups of stars, these are known as constellations, right? And the time of the day and night, of course, is determined by the sun and the moon and the rotation with respect to the earth. The earth rotates around the sun, right? And the moon rotates around the earth. So the phases of the moon, for example, we determine our calendar, for example, the lunar calendar is based on the phases of the moon. And also, for example, we have been using these laws and these phenomena for various aspects of our life for centuries. We've been using them for making the calendar. We've been using them for planning the seasons, the measuring of the seasons, the predicting of the seasons regarding the planting, the harvest, and so on. So you know that, for example, we have the calendar, like the Islamic calendar is the lunar calendar, and then we have the other calendar that we follow. So there are many different, of course, we've been using them for many different, in many different ways ever since human beings have been evolving. And therefore, cosmology, the term that I just told you, it is the study of the origin and the evolution of the universe. So again, you can see some very nice videos and documentaries about this, as I mentioned. And of course, ever since, for example, 3000 years BC, and since then, we have been looking at astronomy. People have been studying it in different ways, and they've been utilizing these concepts in different ways. So you can see very old civilizations like the Babylonians, like the Egyptians, like the Greeks. They have been studying and exploring these topics, and they have also tried to understand these phenomena and also to utilize them in and develop them further. So Pythagoras, for example, we are familiar with his theorem, the right angle theorem that we studied in the last chapter, and the trigonometry. So he also was interested in these studies, and for example, the fact that the earth is round, this was a very major discovery of that time, because before this, for example, people did not know that the earth was round, right? So these were important discoveries. Then you will see many important names that have been, exploring these topics. You can see Aristotle, you can see Plato, you can see many other models coming from the Greeks and many other civilizations. And then one of the important names that we come across when we're studying this is Copernicus, for example, right? So Copernicus also determined the distances of the planets from the sun, and he also noted further how the sun and the other planets were revolving around the sun, and the size of their orbits and so on. So there is a table here that gives you these values. Of course, you don't have to learn these tables or values. Okay, you just have to understand these concepts. Okay. Okay, and then we have another very important name in this field, which is Kepler. Now, Kepler was a scientist who gave us the three laws. These are known as the Kepler's laws. So the first law is that the orbit of a planet about the sun is an ellipse with the sun at one focus. So you know that a circle is completely round and an ellipse is like this, and it has a focus. The sun has one center, but the ellipse has a focus like this, two foci. Okay. So again, like according to him, the orbit was not completely circular, rather it was elliptical. The second law was a line joining the planet to the sun sweeps out equal areas in equal intervals of time. And the third law is that the square of the period, the time period t of a revolution of a planet is directly proportional to the cube of the semi-major axis of the orbit. So this axis is known as the semi-major axis, and then you have the semi-minor axis in the case of an ellipse. So this here, and then you have a very important name, Galileo Galilei. He was an Italian, and he is also known as the father of modern science, because he established a scientific method according to which we do not accept anything without a scientific experimental proof. And he performed experiments to prove that many of the concepts that people were following at that time, that were coming from Aristotle, were actually not correct. And he demonstrated this with his experiments. There are many famous experiments that he performed. And because at the time of Aristotle, it was more of a philosophical discussion and people didn't choose to perform experiments. But now experimental proof is very important. So he was the first scientist to use a telescope to observe planets and stars. And he has made many major discoveries, which include the Saturn has rings, the Milky Way is formed from stars. You're familiar with the Milky Way. Jupiter's moons, the sun spots, the moon has mountains, Venus and the phases like, phases of the Venus like our moon. So he made a number of important, but most importantly, he established the scientific method, and that's why he is known as the father of the scientific method that we follow now. And then Newton, you're all familiar with Newton. Newton also played a very important contribution in this case. And Newton based his work on Kepler's laws, and he developed an explanation for his laws and many other phenomena based on a new fundamental force, which is called gravity. So you're familiar with gravity. So gravity acts as an attractive force between all objects in the universe and decreases with the square of the distance between the objects. So it's inversely proportional to the distance between objects. R squared. The equation is always inversely proportional to R squared. So this was a major breakthrough, not only in understanding planetary motions, but also in the development of theories that underpin modern physics and technology. Perhaps the most dramatic success of Newton's ideas was their use in predicting the position of the eighth planet, Neptune, in the 19th century. Okay, so astronomical distances. You know that when we talk about astronomical distances, these distances are very large. In chapter 1, we were talking about units, right? Units for measurements. And when we talked about this, we were talking about the unit of length as meters. But you know that when you're driving, you're not using meters, you're using kilometers, because you have to find a unit that's suitable according to the length scale that you are measuring. So kilometers is 1000 meters. But then when you talk about astronomical distances, for example, the distances between various stars and planets and astronomical bodies, the distance is very large. And therefore, one of the common units that we use is a light year. A light year is defined as the distance traveled by light in 1 year. So you know that, for example, speed is equal to distance divided by time. And therefore, we can define distance as speed multiplied by time, right? And therefore, this distance, one light year is defined as the speed of light. We take light, the time that light will take to travel this distance. So the speed of light, 3 into 10 raised to 8 meter per second, multiplied by the time it takes to travel that distance. So that's 1 year. So 1 year you can convert it into seconds, and this will be equal to 1 light year. Okay, so you can convert this into seconds, and then you can calculate 1 light year is equal to 9.5 into 10 raised to 15 meters, or 9.5 into 10 raised to 12 kilometers. Again, you don't have to really memorize these values, but you have to understand them. So this is, you can calculate this value by multiplying this, and you convert 1 year into seconds. So you know how to convert 1 year into seconds. So you can convert it and you can multiply it, and you will get this value. So here again, you can see a definition of cosmology. Cosmology is a branch of science that studies the possible ways in which the universe could have occurred. So observations of galaxies in the sky and their individual and combined motion have led us to ask some fundamental questions. So what is a galaxy? I've given an explanation of a galaxy here. You can see a galaxy is a system of millions or billions of stars together with gas and dust held together by the gravitational attraction. So, know, for example, the Milky Way is a galaxy. It's the most familiar galaxy that we know, right? And then Einstein, of course, made a major contribution in this case. We know that he was also working on this, and he explained the universe using his theory of general relativity. Okay, and then there's a phenomena that's known as Doppler shifts. Okay, so Doppler shift is defined as a change in wavelength due to motion. You know, I can share a diagram with you here, and you can see, for example, Doppler shift is a phenomena that's used to understand whether a star or galaxy is moving towards or away from us because its spectrum is Doppler shifted. So therefore, for example, if a train has a lower pitch, which means a longer wavelength, then that is of an approaching train. So light also has a certain wavelength, and this will change depending upon whether the body is coming towards us or away from us. And similarly, you know that red color has a certain wavelength and blue color has a certain wavelength. Therefore, we have terms like red shift and so on. And these are related to whether a star is approaching. An approaching star would show a red shift. Okay. So the greater the velocity of the source, the greater will be the shift in the wavelength. So to visualize the Doppler effect, for example, we can look at, there's a small experiment you can perform in a ripple tank and see a pattern there. Now, when you move your finger across the tank, you continue to make ripples. You will notice that the separation of the wave crest, the wavelength is smaller in the direction of motion of your finger and larger in the opposite direction. So if, for example, a body is moving towards you, you will have a change in wavelength depending upon the direction of motion. So I'm going to share an image that also explains this concept further. So this is an image here. So for example, if you have a car or a train, okay, the Doppler effect for a moving sound source, it is producing a sound. There's a siren here. You will see that if it's coming towards this direction, the wavelength is smaller and the frequency is higher. And if it is going away from you, the wavelength will be longer and the frequency will be lower. So this shifting of wavelength is known as Doppler shift. Okay. Doppler effect is an effect that explains phenomena. It is a change in frequency of a wave in relation to an observer who is moving relative to the wave source. And this is named after a scientist, Doppler. He was an Austrian physicist. So he explained this phenomena. And according to this phenomena, whenever a body is in motion with respect to the observer, you will see a change in wavelength. And when we are talking about wavelengths, there's another figure I can share with you. We can see that for example, we have I will share a figure, new share, okay, and this is showing the wavelengths of the various colors of the spectrum. So you are familiar with this spectrum, right? And you can see that the colors, we have different colors due to the different wavelengths that they have. So here you can see this is red color and this is blue color. So if you look at the wavelength of red color is 650 nanometers and the wavelength of blue color is 475 nanometers. So red color has a longer wavelength and a longer wavelength corresponds to a smaller frequency. talking about this red color here. You can see that this red color has a wavelength of 650 nanometers, and blue color has a wavelength of 475 nanometers. So red color has a longer wavelength. This has a red color longer wavelength, and blue color has a shorter wavelength, and frequency is inversely proportional to wavelength. Therefore, the longer wavelength corresponds to a lower frequency, and the shorter wavelength corresponds to a higher frequency. And frequency is related to pitch, and therefore the pitch of the sound will also be different. But in this case, it's about the wavelength of light. So when you observe the spectrum of a galaxy, whether it's approaching you or it's coming towards you or it's going away from you, you will see a change in the wavelength, and this is known as the redshift. Okay, now I go back to the book. Again, the Big Bang is an important concept that's related to the beginning of the universe, and you must have Hubble again was an astronomer who was studying this, and then we have also talked about the redshift, what the redshift means. And according to his observations, he formulated a small formula which is known as the Hubble's relation, which relates velocity and distance with a constant which is known as h naught, which is the Hubble's constant. So if you know one of these, you can find the other. So you can calculate the distance if you know the velocity, or you can calculate the velocity if you know the distance. So these are different examples in this case. So again, this is another formula that shows you the Doppler shift and distances, and in this case, this is the Doppler shift of light emitted by a moving object, and it's given by this formula in terms of the wavelengths. And you can see that the Doppler shift is related to the velocity of a galaxy that is moving at very much less than the speed of light. So c is the speed of light, which you know is the highest possible speed, which is 3 into 10 raised to 8. And galaxies moving away from us exhibit a redshift. They shift towards a longer wavelength, and the observed spectral features occur at longer wavelengths than in the laboratory. And very distant galaxies, which are moving at a few tenths of the speed of light, use a slightly different velocity relationships. But okay, this is not concerning us. So we can study up till here. Okay, we can solve this example. In this case, for example, we can see that the calcium K absorption line is seen in the laboratory at a wavelength of 393 nanometers. It is observed at a wavelength of 402 nanometers in a distant galaxy. So what is the distance of the galaxy? And this is the value of the Hubble's constant. So we use the formula. Lambda observed is the one in the that we observed here, 402 nanometers. Lambda laboratory is the one that's given here, 393 nanometers, and we divide it according to the formula, and this is the value that we get for z. Therefore, we put this in the equation for the velocity, and we calculate the velocity at this kilometers per second, and then we put the value of the Hubble's constant in this formula, and we can calculate the distance of the galaxy. So you can see how these small formulas can be used to calculate the distance of a galaxy. Okay. This is about cosmic microwave background radiation. We know that these are the radiations that are observed, and they help us understand the Big Bang. For example, they're one of the evidence for the Big Bang. Now, this is a very important equation that we are familiar with. This is E is equal to mc squared. This is the Einstein's famous equation. Everyone, I think, has heard of this equation, even if you're not, again, a physicist. So E stands for energy. The units of energy are joules. M is the mass, and C is the speed of light, which is 3 into 10 raised to 8 meters per second. So this means that mass can be converted into energy. So this is a very important concept that led to the development of fission and fusion. So we see that a small amount of mass can be converted into a large amount of energy because it's multiplied by the square of the speed of light, which is a very high value. So this was a very important, a very groundbreaking, a very revolutionary concept that led to a lot of applications and discoveries. So again, we can use some problems to illustrate how this works. So for example, nuclear fusion and nuclear fission. So fission, what is fission and what is fusion? So fission is a process in which two nuclei, a nucleus is bombarded with a small particle and the nucleus breaks into two more nuclei plus another part, some other particle like neutrons and some radiations like gamma. And in the process, you will see there will be a mass difference that's known as a mass defect, and this mass will be converted into a lot of energy. So this is a basis for nuclear power, for example. That's how we generate nuclear power. Fusion is the reverse of fission. Again, this can be also be used for the generation of power. It's the source of power in the sun, for example. Fusion is happening in the sun. So in this case, fission normally happens with heavy nuclei like uranium, and uranium is a heavy nucleus that can be used for this process. Fusion takes place with light nuclei like hydrogen. So in fusion, simple nuclei are bound together. For example, hydrogen nuclei will be bound to form helium. And again, the mass difference can be converted into a large amount of energy. You can make these calculations. We will do some problems again where we can make these calculations and we can show how this energy is generated. For example, in this reaction, a very small amount of mass difference, which is 0.0287 kg, when multiplied by the square of the speed of light, generates a large amount of energy, which is 2.58 into 10 raised to 15 joules of energy. This is a large amount of energy. So this is the highest amount of energy that can be produced as compared to any other method of energy generation or production that we know. For example, combustion of fossil fuel and so on. They are nothing compared to the amount of energy we can generate by these methods. The fuel consumption in these methods is very low. Again, another unit that we come across when we are talking about this is U. This is known as the atomic mass unit. So the atomic mass unit is defined, it's also known as the unified mass unit. So it is defined as 1/12 of the mass of an atom of carbon-12. So the unified mass unit is related to gram and kilogram using this equation. So for example, 1 gram divided by the Avogadro's number. Avogadro's number, this is a constant number which gives the number of atoms, ions, or molecules in 1 mole of a substance, right? And then this gives 1 U is equal to 1.67 into 10 raised to minus 27 kg. Again, you don't have to memorize these values, but you have to understand how you got them and how you can use them for solving whatever problems you have. Also, we can prove that this amount, 1 U, if it's converted into energy, it's equivalent to 931 MeV. MeV means mega electron volt. This is also unit, electron volt is also unit of energy. So 1 joule of energy or 1 electron volt of energy is equal to this many joules of energy. So there's a conversion that can be done. Normally we use joules, but in some cases we also use electron volts as the unit of energy. And mega electron volts means it's 10 raised to 6 electron volts. So it's a large amount of energy. So these are some units that are important and you should pay attention to them. Okay. So please try to understand these concepts. They are very interesting. They're not difficult at all. Just try to develop an understanding of this. You must have heard of many of these terms before also. So please study this again and you will understand it better. And then when we will use them for problem solving, you will again develop a further understanding, a deeper understanding of these concepts. Okay? Okay?
Yes, ma'am.
Okay. Again, the Big Bang, you must have heard about the Big Bang, right? So that's also an interesting concept. There are many theories about the uh, universe, and the Big Bang model is one of them. And again, every theory has its pros and cons and its evidences and so on. So we will discuss this a little bit. Another concept that we got from Einstein's work was that the universe is expanding. It's continuously expanding. And there's a Nobel Prize also that was given for this confirmation of this discovery. And I've also uploaded some material in Google. You can look at that. So, for example, Big Bang model is one of the accepted theories that we now have about the universe, and it is expected that we are living in an expanding universe which started in a Big Bang. And again, there are theories and there are proofs of these theories. So, for example, the first idea, there are many ideas here. We are talking about two key ideas about the Big Bang. The first idea is that as the universe is expanding, it is cooling down. So it started at a very high temperature and gradually the temperature is cooling down. So it's behaving like a gas. So the temperature of a gas, for example, can be measured using this equation, where K is a constant and T is the temperature. This is the average kinetic energy. K is a constant which is known as the Boltzmann constant. Has this value. So if you allow a gas to expand, it does work, and this work comes from a loss of thermal or average kinetic energy, and hence the gas temperature drops. So using this explanation, we know that the universe is cooling down as it is expanding. In the beginning, it was very hot. It was too hot for any kind of life. Gradually, as it cooled down, then molecules start to form and elements start to form, and then gradually life began. Okay, so that's the theory in this, the model of this case. Another concept in this case is the concept of pair creation and pair annihilation. So our universe is composed of matter and antimatter. So, for example, the electron has an antiparticle, okay, a positively charged counterpart. The antiparticle is a positron, which has a mass identical to that of the electron, and it combines with it to annihilate and produce two gamma rays. So, when an electron and a positron combine together, they disappear. Disappearing means annihilation, and as a result, you have gamma radiation. The process can also be reversed if the energy is sufficient. Two gamma rays can be combined to produce an electron-positron pair. So such reactions are taking place in the universe. So each gamma ray must have an energy which is given by Einstein's equation, and this can be determined according to that the equation that we just discussed. So every known fundamental particle has an antiparticle. The mass of each particle in this table is given in units of MeV. We're using units of MeV as we discussed. This is a common unit of mass used in particle physics, and the equivalence of energy and mass is given by the equation that we just discussed. So mass, for example, is measured in units of energy and then time. So MeV divided by c squared according to this equation. That's why when we're studying particle physics or nuclear physics, this is the unit of mass that we use. And the unit of energy that we use is mostly MeV because it's a large amount of energy. We're not normally using joules. Okay. So we will again study these concepts and apply these concepts next time in the class. So please do go home today and spend at least 1 or 2 hours studying these concepts. Okay. So this is the last chapter of this course, and we have when we complete this chapter, then we would have completed the course. And you also look at the next assessment that you have and prepare for that assessment. Okay.
And then what are we supposed to read in the maths?
I cannot understand what